Again. Okay. So I think I've sort of hinted at this already. You can see that, right? We're on screen, right? I think I've already hinted at this, that this is an important area, and thought it would be the last area that we should cover in the sort of more formal section, the first 5 weeks. Of course, we're going to the sort of guest lectures where you'll see examples from next week, is multi-fidelity modeling. So what does that mean? Okay, so you should recognize this slide from before. So in this slide, the idea is that you've got the real world, you've got a series of statistical emulators, and you've got simulators. And the idea in multi-fidelity modeling is that you're going to use, as this sort of implies with these little links, these spider legs coming out of the statistical emulators, to relate different data sets. So you're getting this one here in reinforcement learning parlance, people would call this sim to real. But whereas that's been a thing in reinforcement learning for like 6 years or something, it's been a thing in uncertainty quantification for a lot longer. So this one's trying to adjudicate between this simulator here and the real world data here. This emulator here is sort of adjudicating between one sort of low fidelity simulation, the small box, and a high fidelity simulation, and then trying to relate them to the real world. And that's the idea of the sort of multi-fidelity emulation. So the first approach I want to introduce, and I think that this is, I don't know if they were the first, I suspect this type of thing has been done multiple times, but there's a paper by Mark Kennedy and Tony O'Hagan from 2000, which is in your notes, where this is how they propose to do that. And Tony O'Hagan's sort of one of the originators of Gaussian process models in some sense. So it's no surprise he also chose to do it with Gaussian processes. So the idea is that you've got some high fidelity simulation. And what you're saying is that that's corrupted from some relationship between a low fidelity simulation and an error. And now what we can sort of map this to is a sort of chain setup where what we're saying is that the high fidelity is given by a linear mapping of the low fidelity. So this is, in this case, rho, and combination with this error term. So this is nice because what it turns out is if we build things like this and we declare everything on the right-hand side a Gaussian process, then everything on the left-hand side becomes a Gaussian process. So in this case, what we end up with is a challenge. And typically, okay, so I should just re-emphasize, going back to these plots here, the smaller simulators, the low fidelity ones, they're lower quality, but the idea is that they're presumably cheaper to run. So in sort of Formula One examples, you might have two different types of CFD. You might have computational fluid dynamics, which is sort of being run at a very broad grid. Remember, we looked at that for weather simulations. And then you might have one that's being run at a very fine grid. And then you might have the real world, in that case, might be the wind tunnels, not even real world, sort of a testing model. And you're trying to make decisions about whether you should run the low fidelity computational fluid dynamics model, the high fidelity computational fluid dynamics model, or do something in the real world. Okay, so here we can think of X as perhaps being some design points for the low fidelity computational fluid dynamics model, and X high being the sort of high fidelity fluid dynamics model. But the nice thing about the sort of O'Hagan layout is that you now get a correlation between your low fidelity and your high fidelity Gaussian processes. Now I'll try and sort of say this slowly. Do sort of drop questions in the chat if you're curious about what I'm trying to say here, because I think this turns out to be strikingly simple. But initially, like a lot of stuff in Gaussian processes, I think once you realize what's going on, it's like, oh my God, that's obvious and simple. But when you first see it, because it's not the sort of thing that happens in other types of models, it perhaps takes a bit of time to digest. So the obvious and simple idea is that the way you model, well, given the definition we have from before, we can write down, because the high fidelity and the low fidelity Gaussian processes were linearly related to each other, we can write down a joint covariance across the two functions. So what you're seeing on the left here, the idea is you've got function 1 is stacked above function 2, where function 1 is the low fidelity, function 2 is the high fidelity, just as we stacked our designs here. And then you have what sometimes is called a multi-output Gaussian process, or sometimes a multitask Gaussian process. In geostatistics, this is called co-regionalization, and geostatistics, we're talking about it before, or co-cridging. And what you're seeing in the covariance function here is that the covariance function ends up now being sort of in blocks. So this K is kind of representing, it's slightly sloppy notation, as it normally is with Carl Henrik and me. But the idea is the sort of K low in the top left is just the covariance of the low fidelity covariance function on its own. So in the top left, we have K low. And if you ignored everything else, ignore the high fidelity, that's giving you the covariance function of your low fidelity. But because of this definition here and the properties, this one here, right? So look at the F high is equal to F air plus rho low. Because of that definition here, that gives us this covariance function between the two. So what it's saying is, look, I expect the high fidelity. So actually, if we just look at this thing here and say, well, what's the covariance function for the high fidelity? Well, it's going to be the sum of the covariance function for this plus the covariance function for the error plus the covariance function for this term here, which is, sorry, the rho times F low. Now, that's going to be the covariance function for F low times rho squared. So that's what you see in the lower right block here, is the covariance function for the high fidelity on its own is rho K low plus Kr. So if we were just looking at those two functions independently, then that's just the covariance function we'd see. But the key important bit is the cross covariance. So now there's these two terms here, which are giving us the correlation between these two functions. And because of the way we've defined it, that cross covariance is given by rho K low. That just comes from the properties of multivariate Gaussians. Okay, so this is the sort of new Gaussian process model. And then what I just want to sort of say briefly is how we build such a model in Emukit. So in Emukit, and this is an idea that went back to GPy when we started building. So the first set of multi-output Gaussian processes I worked on was in MATLAB, and I wrote a load of code to do them in MATLAB, and then we totally changed the way we do that in GPy. I didn't write most of the GPy code, that some of it was based on the MATLAB code, but we did change the way you're doing multi-output Gaussian processes. And the key thing is to realize that the index for the output goes on the input, okay? What do I mean by that? Well, it's showing it here, right? So the way you build these multi-output or multi-fidelity things is you label on the input which fidelity you're interested in. So here we've got a sort of design point where we've got 3 dimensions for the design. We've got the low fidelity, and there's 3 data points associated with the low fidelity. And then we've got 2 data points associated with the high fidelity. But notice alongside that on the input, we're putting an index which is saying whether it's low fidelity. Low fidelity is 0 and 1 for high fidelity. Okay, why is that? Well, if you think about it, and actually I often think, it's a shame I don't have a board here, because suddenly I'm thinking what I want to draw for you is if we think of these low fidelity and high fidelity, let's think of this being F subscript 0 of H, where H in this case is, I don't know why I've got H there, is X, and F subscript 1 of X instead of H here if we think of it as that, those are the two functions here. You think of the subscript of this function, I'm just absorbing that into the bracket. Yeah. So remember that Gaussian processes are just continuous versions of Gaussian distributions. So this thing inside the bracket is always the index anyway. It's just a continuous index. And all we're doing is saying, well, when we got discretely separate functions, whatever we're indexing down here, the low or high, can also be thought of as being absorbed into the input. So you, like the whole, just think of the whole index as sitting in the bracket. And then this makes sense because you've got this, I mean, H was the design, but you've got these different separate inputs of that, plus you're augmenting it with what function you're interested in. So you're asking the Gaussian process, which is now a joint Gaussian process over both high fidelity, that's between low and high, low fidelity and high fidelity functions. You're asking it to give you the output associated with the low fidelity or the output associated with the high fidelity. Yeah, so that's I'm not sure. It is weird, Daniel. So Daniel's asking, do we really assume that the feature spaces for high and high and low fidelity simulators have the same dimensionality? Isn't that slightly weird? I guess I see a bit where you're coming from there, Daniel. I mean, you don't have to do that in the base case, but I think what you're sort of hinting at is maybe shouldn't the high fidelity have more to it, more information in there? Yes, but very likely. But remember, when we're doing the design, we don't necessarily put all that information in our covariance function. All we care about is the question we're asking of the low or high fidelity simulation. And that is quite likely to have the same initial state. We can do it with different dimensionality. We can do things like that as well. It wouldn't look like this matrix. I couldn't draw it like this matrix if we were doing that. Cool. Okay, so the most important function in the world of surrogate modeling, the Forrester function. So just as an example, what's showing you here is a multi-fidelity version of the Forrester function. So the idea here is that you've got some high fidelity version of the Forrester function, which is the cyan curve, and some low fidelity variant that you also hope to get information from. Now, always try and think, it's never going to happen in the examples we're doing, but always presume that somehow the low fidelity one's cheap, right? That you can get samples from that very easily, and the high fidelity one's expensive. Otherwise, you would just get information from the high fidelity function, right? There's no point in the low fidelity. So there has to be some sort of cost difference to what you're doing. But what we're seeing here is you've got these two sort of functions, and what we're seeing is a sort of set of design points. So if you just see where the dots are, the cyan dots and the yellow dots, that's a sort of an initial design that's coming from the low fidelity and high fidelity functions. And what we've got here, and of course, as ever, this is in your worksheet for this week, what you'll see is a fit, the Gaussian process fit to the low fidelity and high fidelity. Now, the fit, we've taken enough points from the low fidelity function that you don't even see error bars on that fit, right? So on the low fidelity function, you see no error bars. But what's kind of interesting on the high fidelity, so this is the fit to the low fidelity here, you see no error bars. What's interesting on the high fidelity is it's sort of, the model kind of has no data in this region here, but it thinks something's happening. The reason it thinks something's happening is because it can see something's happening in the low fidelity. So it hasn't got quite right what's happening, right? Well, it's within error bars, right? But there's no data in this region on the high fidelity. But because it's correlated across the high fidelity and the low fidelity, by the way, rho is now obviously a covariance function parameter. So rho is giving you the sort of extent to which you trust somehow the low fidelity function, right? If rho was 0, then you would just be looking at independence, right? So the worst case rho becomes 0. So whatever rho value is probably slightly wrong here. And what we're seeing is that it's slightly overestimating the mean of where the high fidelity part is, right? But you can see you can share information now across the two functions, just fitting that covariance. And if we go to if we look at what a standard model would have done, you can see if this here, we've got two sets of error bars showing on this. So there's the model we've just seen is the blue dash. So we've dropped the low fidelity part of the image here. What we've just seen is the model that was the blue dash. And then what you're seeing now is also, and you've seen this plot multiple times before, is the white dash line is if we just ignore the low fidelity. If we just independently fit a high fidelity GP, ignoring the low fidelity on it. So the blue dash is the multi-fidelity model. The white dash is the I'm just going to fit to the high fidelity data. And you can see the difference, certainly in the error bars and actually also in the functions. So the error bars for the high fidelity GP are much, much wider. They're going all the way down to -15 and up to 15 at the top. They're lower, much lower. So it's got a sort of better idea of where the function is. Even though the mean is more different, it's got a better idea of what the function is looking like. And that's the idea. How do we encode our belief about how much worse the low fidelity model, how much more expensive the high fidelity? Right, great question, Ben. In this model here, the row is effectively, well, let's go even further back, right? If row was 0, then we would just lose any information from the high fidelity. We'd just be saying that F high is basically all error. And error in this case is not error as in noise, it's error as in the difference between the low and the high fidelity functions, right? So if we set row to 0, then there's no signal from the low fidelity function at all. So row is like a trust parameter. It's, the larger it is, then the more likely, the more you're starting to trust the low fidelity function. How do we encode how expensive the high fidelity is? Well, that's going to be your acquisition, right? So that's not something we're looking at. Actually, I'm just realizing it's probably not in the lab, and it's a good question. Thanks for asking it. But that will tend to come in when you're making a decision. So like you've got to make a decision between a low and a high fidelity. You've got to encode the fact that it's more expensive. So it's your decision comes when you build your acquisition function. So you include that type of cost in your acquisition function, right? That it's going to cost you 10 times as much to do a low fidelity, sorry, a high fidelity call over a low one. So Janek's saying, with the multi-fidelity modeling, we have a better uncertainty estimate, but a worse mean function. Is that always the case? It's not always the case. And I think you just have to be very careful about over-interpreting what the mean function's doing, Yannick. So it's, yes, the mean looks slightly worse, right? Because it's closer. But look at the size of the variance, right? It's basically saying, I tell you what's happening in this regime is basically the Gaussian process saying, I don't know. I'm going to revert to the prior. So it's just coincidence that the function happens to be closer to the prior here. And actually the sort of fact that there is some information and it's pulled itself up is indicative that the row is probably slightly wrong, right? It's overly trusting the low fidelity model. One could try and deal with that with some uncertainty. But look, I mean, the key point, Yannick, to think about, and I would suggest this is true, although I don't have a proof in front of me, is if we were to look at the probability of the true function, cyan, under both the linear multi-fidelity GP and the high fidelity GP, I suspect very, very strongly that it would be higher, the actual location of the mean function would be higher probability under the linear multi-fidelity GP, because although the mean's slightly off, the error bars are lower. And so this is a very diffuse Gaussian at this slice at around 0.6. I'll just get the mouse on there. So if we're looking at this sort of point here, the Gaussian, your mean, as you're saying, yeah, is slightly closer, but this would be a very flat Gaussian, right? Its standard deviation, it looks to be 2.5 times as large. So if you picture this Gaussian, you've got to picture the blue one being quite a peaky sort of thing sticking up, and then the white one is really, really flat. So I suspect you'll find that the probability of the truth under the white Gaussian is actually lower, although I don't know that for sure. It's like, I suspect Biden will win the election, but I don't know it for sure. But it's that sort of probability. Okay. So there's an example of doing this that you'll work through on the worksheet. But there's also sort of it's obviously not a panacea, because, why should we necessarily assume that the low fidelity is linearly related to the high fidelity? And this is an example that Andreas Damianu came up with to demonstrate when this model fails. So here we've got a low fidelity function, which is just the sine of x. And then we've got high fidelity that is related, but it's non-linearly related in a sort of funny way. So it's related to the low fidelity, but then it's the low fidelity squared, and then it's multiplied by x. So if we plot it, this is kind of what it looks like. So there is information here. I mean, this is kind of like quite a complex situation, right? There is information here about the high fidelity, which is the cyan, from the low fidelity, right? There's some sort of shared information across the period. But the low fidelity is doing something very different at certain points. And if we plot, so if we think of the high function, if we think of the high fidelity function is like a nonlinear corruption of the low fidelity, then this would be what the nonlinear corruption looks like. So if we were to plot the previous model, we would just see a linear relationship plus some corruption between the two. But look at this highly nonlinear relationship that Andreas has effectively constructed. On the left axis, sorry, it's just fallen off the axis. This should say high fidelity. And then on the y-axis is high fidelity, HF, and on the x-axis is low fidelity. And then what happens in this case, if we try and attempt the linear multifidelity model, well, everything gets confused. So what actually happens if you try the linear multifidelity system is it gets it wrong. Basically, it has some sort of compromise between the two situations. So here's the true function, and here's the linear multifidelity. So in this case, the high fidelity GP would definitely do better because the assumption is just plain wrong, right? And if your assumption is wrong, you shouldn't expect your model to magically, if you've hard encoded such assumption, to fix things up. So what it's sort of done is it's found this compromise. It's got this sort of design points here, and it's decided, aha, well, but I really know that the low fidelity is doing this sort of slower period of oscillation. So where it's got the design points from the low fidelity, it's got more design points from the low fidelity because they were cheaper. It's decided to cut through and totally miss the, so here you can see it's cutting through beautifully the design points, and then outside the region of the design points, it's massively confident about the wrong thing. So, this is the problem with a model-based approach. If you put a model in and it's wrong, you're effectively undermining your system. So you have to be very careful about your model-based approaches. So in this case, linear multifidelity is not a good idea. So the alternative is then that you start doing nonlinear multifidelity modeling. So in nonlinear multifidelity modeling, you say that your high fidelity is now a nonlinear function. So rho is now a function instead of just a scalar. A nonlinear function of your low fidelity term plus some independent corruption. And the challenge with this is that the low fidelity is, if that's going to be a Gaussian process and this is a nonlinearity rho, then this is no longer a Gaussian process. So unfortunately, we lose the analytic tractability. But despite that, you have an example where you're going to do it in the worksheet. Okay, and this is that example. This is so where there's nonlinear relationship between the low and high fidelity, and that's been learned in this case by the nonlinear multifidelity model, which is a lot more complex thing to do. So the sort of linear multifidelity is simple, and the nonlinear is much harder. Right, and then here we have that it's learning the relationship. So bear in mind that function rho is is a function that learns the relationship between the two, and you can see this is what it's learned. So it's slightly off, but you can basically see that it's managed to understand that relationship. And that's a nice example from this person whose picture I sort of saw that and I wondered if I should fix it, but I quite like the fact that Andreas is just poking through his circle in this picture. So Andreas, this is actually a lot of the pictures I'm sharing are pictures from when people did the work. Andreas is a little bit grayer in his hair now, but he's a longtime collaborator of both Carl-Henrik and mine. He's actually still at Amazon. He worked with us, with me and the supply chain team there. And the reason he got into this sort of nonlinear multifidelity optimization is because he's also the sort of PhD student that worked on this notion of deep Gaussian processes. And I just wanted to sort of use that as an excuse to sort of say a little bit about where those models come in an interesting way here. I mean, I think it should be immediately, if you know about deep Gaussian processes, if rho is a Gaussian process and f low is a Gaussian process, then this is a sort of composition of Gaussian processes. One Gaussian process is feeding into another, and that's what we call a deep Gaussian process. So that was what Andreas's PhD thesis was about. And then the sort of things that you then are interested in, if you can do that, is you can do all sorts of things like this is a supply chain example that I've shown before, that you build a set of statistical emulators of each component. So this is your demand forecast. You're going to emulate that. You emulate your supply forecast. You emulate your cost predictions. You emulate your purchase order. But then you can chain those emulations together. And then what you've got, if each of those was a Gaussian process, you now have a deep Gaussian process to emulate your system. And that's something that's been in our minds, and we've done a little bit of research-wise. Other people, I think, have started to spot it as well. But it's what I call deep emulation. So you see, you can even use the D word in this domain. You know, you can always tell people you're doing deep learning and get expensive job offers from companies that don't know any better. Because you can do deep emulation. So that's something that I'm actively interested in from a research perspective. So I thought I'd just mention that. Okay, so I just wanted to do a sort of brief reflection on what we've been trying to do across this module. And I think we should set up a way of you giving us some feedback quite soon as well, maybe through a separate form. Because of course we're doing it for the first time and we're just sharing material that I think we're passionate about, that we know deploys well in the real world. And what we're trying to do is give you this sort of toolkit of surrogate modeling, because I think many of you, if you're certainly those of you who are auditing the course doing PhDs, you'll already be imagining ways in which you can do things with this in the physical world. Those of you who are on the MPhil or part 2, you may be interested in things for your projects. Or you may just sort of be enjoying this slightly different perspective on some concepts that are familiar in other parts of machine learning. And what we're trying to do is give you this sort of toolkit of surrogate modeling. So give you the ideas of the different things you can do. Now, when it comes to project work, we want you to sort of use your imagination. We're going to try and help stimulate that imagination through the guest lectures and through your input. Remember that you've got the opportunity to share your interests with us through the Google form on Moodle, the Google on Moodle. You know, we'll try and set up some interesting projects where you get to sort of flex your muscles, combine some of these parts together. But sort of also partially to sort of inspire you the sort of things that can go on in a very relatively simple way. I just wanted to introduce this mountain simulator example, which is just going to compose a couple of different emulators in a different way, and also show how you do Bayesian optimization in EmuKit, because Carl-Henrik did it in GPyOpt. But of course, you can naturally do it in EmuKit. So, oh, I probably have these slides the wrong way round. So let me just show you Mountain Car. So Mountain Car, this is originally an example that was built. I've rewritten it for EmuKit, but it was built by Mark Pullin, who worked with us at Amazon, and Javier Gonzalez. Not the simulator itself. The simulator goes way back. It's like when I started in machine learning in 1997, reinforcement learning talks would always show mountain car. And the thing about this challenge is you've got this little car that's represented by this trolley here, and it wants to go up this mountain to this flag. But the poor little car doesn't have enough power to get up to the flag. So if the car just drives up this side of the hill, it doesn't get very far. It becomes overwhelmed by the steepness of the hill. So what the car has to do is actually has to go up the other side of the hill and build some momentum and then accelerate up. So it sort of has to build. So it's a sort of interesting sort of reinforcement learning challenge, because when you're exploring the state space, you have to realize that the right thing to do is start by going in the wrong direction. So the reward in this case is we have to have a continuous reward because we're trying to do Bayesian optimization here. So the reward is the car scores in terms of how close it gets to this flag in a quadratic way. Now, this is been around, as I say, for 23 years, but it's also available in OpenAI Gym. And so the other thing about this exercise is we're using OpenAI Gym, which has a number of different simulations that you also might want to have a look at and play with. But I just want to sort of dig down a little bit in this very simple simulation about what's sort of actually going on. So here is the simulation, the orange box, right? So there's a mountain simulator, right? But within that simulator, you also simulate the dynamics of the car. So the mountain simulator is like gravity is applying to the car when it's in certain positions and doing things. But within that simulation, you also have a little dynamics model of what the car can do under instructions. And what you're basically going to see, so we're going to do a couple of things in the lab, which I'll just sort of overview now. The first of which is the you can fit a controller to the car. So the controller says, the controller basically has what in reinforcement learning is called a policy. It looks at the state of the car and it says, given your position and your velocity, what action you should do. And the car has two actions. It can either accelerate left or accelerate right, right? So that's the controller. So that the parameters of the controller, there's three of them. One is the sensitivity to velocity, one is the sensitivity to the position, and the other one is the offset parameter, right? And then you can just compute a threshold as to whether you accelerate left or right. And that's all that the controller does, right? So there's three parameters in this system, and those are the only things we control, right? So we can optimize over these three parameters to try and get this car out of the mountain. And that's basically, we're converting that to a Bayesian optimization problem, okay? Now, within the simulation itself, there's in inverted commas, very simple physics being applied to make things happen. So, so this is the sort of physics. The car dynamics are driven by its position at any given time is given by its position at the previous time step and a function of the action force that it includes. And that action force is something that's coming from the policy. So there's a position and the velocity. And as I said, the policy is very simple. It's just an offset and a scaling of the position and a scaling of the velocity. And the car then responds from that. And the aim is to try and get the maximum reward out of the system, which is achieved by, in our case, doing a Bayesian optimization to find the set of parameters of the controller such that we maximize the reward. So the reward is 100 for hitting the target minus the squared sum of actions, right? Okay, so let me show you. This is what, if I put a random, so in this case, you can do a random design. And so you start the system with a random initial design. And this is like what one of the points of that random design looks like. So bear in mind, this is 1 point, right? So we've just selected a random weighting from the design space of these three parameters that are the offset, the position, the velocity. And then it's just showing you the result of that, right? So that this is how it's responding, just bumping up and down. Now, the first thing you do is just apply Bayesian optimization to the simulation, right? And when you apply Bayesian optimization to the simulation, this is what you get. So you can see that the car manages to build some momentum. It goes up the right.
Can't see things though.
Oh, right. Sorry. When I play, yes. Yes, sorry. Thanks for pointing that out, Colin. Yeah. I need to click it on here. So this is this is the random. So this is if you just have random optimization. Random optimization, a random design point. This is one of the design points. So doesn't do great. And this is the best controller after 50 optimization. So there's 25 design points we use in this case. So 25 points in the initial design. And this is the best controller after 50 iterations of Bayesian optimization. So it's sort of explored that space and it's found a set of parameters that get the car over the hill. Now, both of these, by the way, both of these things are terminating. If they don't succeed, they terminate after 500 time steps, right? So the car simulator, which is in effect inside this loop, is being called 500 times for every failure, right? Now, in this case, the car simulator is trivial, right? But imagine that the car simulator is really complicated, that it's a nasty piece of work and, is taking a lot of time to simulate what's going on in the car. Okay, so if the car simulator was very complicated, then what we could do is we could emulate it, right? So this object here, I'm saying, well, imagine this is really a complex simulation. So instead of just a simple like car goes forward, car goes backwards, we've got some really complex physical model. What we can do is we can use a Gaussian process to model the different parts of the simulator, right? So what we're going to do in this next example is do that. So instead of running the simulator 500 times, and we're not doing acquisition here, we're just doing model-free initial design. It's very, very simple. You could improve what we're doing by doing model-based experimental design on this component. There's something you can play with, right? We're not going to do that. We're just going to say, I'm going to do an initial design, which is a random initial design, to fit an emulator to the car dynamics specifically. Okay, so I'm going to just do a random initial design, take 500 randomly selected points to train emulators. And this is what I get. So this is the emulator I have of the position and the velocity. Okay, so now I've built Gaussian process models, and there's some inaccuracies in them as well. They're not perfect, right? Gaussian process models that show me over time. Here I'm using the emulator and the simulator. So you can see over time the inaccuracies get greater because here's the controlled input and here's how it thinks the car would respond, right? Which isn't quite right. But I've got a Gaussian process. Now, okay, the interesting thing here is I've got a Gaussian process emulator of this object here, the car dynamics, which is called as a subroutine within the overall simulator of the mountain car example. Of course, the car dynamics are so simple that my Gaussian process emulator is actually a lot slower than the car's real dynamics in the real world. But we're pretending that this is a very complex set of dynamics, right? Okay, so now what I've got that is our emulator was built using only 500 calls to the simulator. But to do the Bayesian optimization before, we did 25 initial design points, each of which required 500 calls to the car dynamics, because one call to the simulator leads to 500 calls to the car dynamics. And then we did 50 Bayesian optimization points. We perhaps could have done fewer, I didn't check. So overall, we did 37,500 calls to the car dynamics. And this comes up, this is the sort of thing that comes up. So it would come up a lot in the supply chain. So if you're trying to sort of simulate Amazon's supply chain, as part of the subroutines of that, there's other things that are simulators themselves, right? And those things can be slow, and your overall simulation of the supply chain gets really slowed down by this. And I mean, there was a particular example of something we were doing in that space where we ended up emulating a simulator that was within the overall supply chain simulation, and was a slow component. And we did such a good job emulating that simulator that they actually replaced the simulator in production with our emulator, if you see what I mean. So basically, there was a simulator running in production, and we were trying to sort of recreate what's going on in production. And it was making a very important decision, something that happens every time you load Amazon's website. And then when we emulated it, because we were trying to build a simulation of the supply chain, it was such a nice job done around that they actually ended up shipping our emulator in production instead of the simulator, because it was that much faster. So they could explore more possibilities with our emulator than what they were doing with the simulator. So you get sort of, when you're working in the real world, you get weird effects like that. Here, instead of training on the entire simulator that whole time, all we're doing is we're going to use the best controller using the emulator of the dynamics. So we're not training on the simulator, really, we're training on the simulator. So this is what this sort of plot was supposed to be showing. We're doing, so I can try and explain this plot a bit better now. So what this plot is showing is, look, this is the real simulator with a car simulator inside it, right? We've now built this emulator, which is modeling the car dynamics. And then we've got this sort of new system, which is where we're not running this simulator anymore, we're running this emulator. So I've drawn this alternative box around it. So the first thing we did is Bayesian optimization on the original system, which is this surrogate model here doing the Bayesian optimization. But now we're doing Bayesian optimization on this new system, which is part mountain simulator, part emulated car, right? And then we're going to do Bayesian optimization on that instead. Yeah. So, and you know, imagine when you get a complex system, how much of this stuff you can do. So, you know, basically you end up profiling your simulators and deciding which one's the slow one, and then you replace that with an emulator and see if you get the effect you want. So here it is. Here's the result. You know, I don't think you'll see much difference from the one with without the emulator, right? Works fine. Of course, that's not.
Can't see it.
Oh, sorry. Yeah, I keep forgetting I do it on the wrong. What's going on is I'm actually controlling the slides from a different screen, so that then I forget to. Oh, there it is. There it is. Sorry. So this is the yeah. You won't see much. There's no difference really between that and the thing you saw before. Okay. So an exercise for the reader, apply multi-fidelity optimization in that scenario. And the last thing I kind of wanted to share with you was this, because we didn't just work in the supply chain, but we also worked, I can't, you know, unfortunately, I can't tell you exactly what we did on this system here, but just to introduce, this is the Amazon's Prime Air delivery drone. I often sort of say that one of the interesting things about working at Amazon, you know, if you ever watch this film, Arthur Christmas is like this film about what it would be really like. It's an animation. It's not a real simulation of what it would be really like if Father Christmas had to exist and deliver presents to everyone across the world, what logistical operation that would look like, which is a sort of, you can imagine, it's quite a big logistical operation. Well, that's kind of what Amazon does. So Amazon is not delivering all the presents, but it's delivering such a significant number of them that it has this enormous demand on its systems in the fourth quarter. Right about now, right? They'll be all boiling up. All fulfillment centers across the world will be full. And there's weird things like in Spain, I don't know, there's 3 different peaks or something because people get different presents at different times. So they're always looking to innovate on that supply chain. And with that in mind, I think of this as Santa's sleigh, because this is the Prime Air drone, which is, I think the current state is it's being operationalized. So basically, this drone that we're going to watch this video of, hopefully the video will, So I've done the same mistake again. Here we go. This drone that we're going to watch the video of over here is vertically taking off. Now you see it's got this odd shroud around it, makes it look like a TIE fighter. Watch what it's doing now. It's going to a horizontal flight position, right? And this is important. And I've seen that they publicize these figures in the end. In order to make it productive, it has to have like a 20-kilometer range on battery. And so this horizontal flight it's doing now, these surfaces here are flight surfaces. So the one at the top, the reason it looks so crazy like a TIE fighter is because the flight surfaces don't need to be as big as you would expect because it's taking off vertically. Most of the lift you normally need in a plane is for takeoff. So it ends up with this ability to fly with very narrow control surfaces, which is the top and bottom. The other two things are shrouds and structural. Now, what you see it's going up now is it's going to land and it's going to transit back into a vertical position in order to land. Now, these people at the top, Gur was the vice president who came up with the project who led it. Paul is the sort of chief scientist for Prime Air, and David was our collaborator. And I can't say exactly what we did in it, but you can imagine why I think that's such an important project is because it involves several things. It involves the need to sense. I mean, so they talk about this sense and avoid system publicly, like about how it detects what else is in the air and avoids it, or how it detects not to land. There's a load of computer vision needed for that. Because this is, right, it's a drone that's that's fully autonomous flight, right? It's not being flown by anyone in that case. But also it needs these sort of very interesting capabilities to go from horizontal to vertical and vertical to horizontal, which is a difficult maneuver to do. There's lots of ideas about how you do that, but it was also something that my team got involved with helping. So when I watched that video, I mean, I don't know whether we should have drones flying everywhere or not. I'm not certain about that, but just knowing what's going on in that thing, it actually makes me a little bit emotional to know all the elegant machine learning. Many of the techniques you've learned about that are needed to make that happen. So I wanted to end there today, and we'll do our usual thing and stop sharing and see if there's any questions, or we'll just ramble.